Okay, so this is the 6th week. It says here on the syllabus. And there's a lab this week. And what we're going to do today is finish chapter 4 on piezoelectric materials. And that's just going to take a little while. So that we'll do the first 2 problems on the problem set, and then we'll finish the problem set tomorrow. We're following the syllabus, right? And then we'll begin the piezoelectric ring vibrator. That's one case where we can derive everything explicitly, what's going on, as you'll see, with effort. Okay, so we were talking about other piezoelectric materials. What does other mean here? It means other than the standard ones, which are PZT and barium titanate. And people have entertained just all kinds of possibilities for transducers. It shows you how important I think transduction is in general. And we looked at some of these things here, and I think we finished with this antimony sulfur iodide. So next is lead titanate. So this is PZT without the Z, without the zirconate, okay? And it turns out that it looks like it's useless because when you make the ceramic, you have to heat it up. When you cool it down, it tends to crumble. So you would think there's no hope there, but people don't give up easily here in this business, as we've already seen, and we're going to keep seeing in this course at times. They've looked at alloys, okay, to try to, so that it won't crumble, maintain its strength. And so Brian tells us that that was being done at the time, so this is late 80s here, early 90s. So why would they be doing this? Well, it has a large piezoelectric coupling factor, and it has other advantages that could lead to hydrophones that don't require being segmented. We talked a little bit about segmented in that picture. This is where you the actual material is cut into different pieces that are then put together, or you have conducting strips. We're going to talk a lot more about this later on in the course. Actually, we'll get into in depth into the mathematics of that, because it's routinely done. So here in this case, what people see is or at least saw back then, is the possibility of they could solve this basic problem in the beginning here. They may not have to segment a hydrophone, for example. There are composite ceramics. Okay, now what does that mean? That means that there's a piezoelectric active material, for example, PZT, and then there's inactive materials that are mixed in there in the ceramic process. For example, flexibles. There are flexible ceramics that are piezoelectric. There's actually piezoelectric rubber compounds. So this has an advantage. The flexibility has an advantage. You can imagine one, you can mount this on the hull of a ship or a submarine. Yeah, we don't need to worry about this. And going along with this flexibility idea, there are piezoelectric polymers. So these are organic materials. Organic materials are usually, complicated molecules that have carbon in them. And there are these materials, and I've heard of this. I heard about this I remember in the 90s, PVDF. It stands for this. There are long polymers in there, and it allows it to be flexible and keep its integrity due to the long polymers mixed in with the crystalline and amorphous regions. And the material's polarized, and you can stretch it. Sometimes it is stretched, and it's available in these pretty thin thicknesses here. It's not as transductive. The piezoelectric constants are smaller than those of normal PZT, but it has this flexibility, and it's very durable. And it doesn't have a lot of mass. The density is small. And it has a good impedance match with water, which is beneficial. So people have just, tried just about everything. And this is this is what, I don't know if I got this from Brian. I think this, I don't know currently what they're using, okay? I can't remember. But it's easy to look these things up. All you got to do is just go to Wikipedia, right? And I did that twice this morning, but I didn't get to this. But it can be used. It has been used in small microphones, for example, earphones, medical ultrasonics. And look at this. I don't know if this is whatever came of this. If you guys know anything about this, look at this. At the time of writing, it was developed for ships. Anybody heard anything about this? Yeah. It may be there, just you don't know about it. But you're going to think about it the next time you encounter it, right? Okay. So there are these negative effects that you need to be concerned with in sonar, and we will get more, I keep saying this, more in depth into these later on in the course, but I just want to mention some of them right now. There's one problem is this, and we've already actually discussed this briefly. You cook up this ceramic, it's a material that has these domains, right? Where you have essentially complete polarization, electric polarization, where the dipole moments are all aligned here. It's essentially 100%, very close. And they're randomized, so you don't get any, it's not useful for transduction material. So you have to polarize it. So you have to hit it with a sufficiently strong electric field. And you would think that what you're doing, when you do that, you would think that you're changing. These are all they're locked in. You're not going to change anything in this domain, but you would think that you can reorient the domain here, right? Orient these things so they're all in one direction. Now you have a useful material. It turns out that's not the way it works, and it's similar to the magnetization, ferromagnets. And what happens there, and this is in Griffith's intermediate level electromagnetism book, as Mark can tell you. Right? Anybody else? What actually happens is I think it can happen because there's this effect, I can't remember the name of it, where if you put a sensitive microphone on this when you're polarizing it for magnets, you can hear noise. What's that?
Snap noise?
Yeah. I've heard of that. I've never actually heard it. But so you might think the snapping is due to these things, but what Griffiths tells us is it's the domain boundaries that move. So, for example, let's say you have this, so this is what I think is going on, I'm not really sure. You have this applied strong electric field here. What happens is, so this one's already pretty much aligned. This one's not aligned, but this domain boundary can move. So this becomes kind of absorbed in that. It's motion of the domain boundary. Apparently, it's responsible for this. But there could be sound associated with that motion of the domain boundary. So I'm not sure what you're hearing when you hear that. Whatever that effect is, God, I haven't thought of this in years. It's got somebody's name attached to it. It could be, the reason I'm kind of interested is it could be a lecture demonstration, right? It may not be that hard to do. So anyway, I'm sorry, where were we? We up here? Yeah, okay. Now, to do this process, you have to, as I mentioned to you before, this has to be a very high electric field. So it changes the material. It changes the elastic properties and electrical properties because it's such a strong electric field. But you say that's no problem because it's just going to change the equilibrium, and then we operate about equilibrium and it should be fine, it should be linear. Well, it's not that simple, okay? Let me make sure you get the idea here. Suppose I have a spring, right? Here's a spring, and I overstretch it. I exceed the elastic limit. So it comes back to the unstretched length, and it's now longer, right? Well, is Hooke's law valid for the new spring? Sure. It's just the spring constant has changed. It's still going to be valid. You've changed you got a different spring now. Think of it that way. Okay? So, Hooke's law will be valid for this new spring. Okay? And over some pretty good, springs have a pretty good linear region. Okay? So as long as you don't exceed the new elastic limit, you're fine. So you might think the same thing is happening here, but it's not true. And the reason is actually interesting. This strong electric field that's put on here causes micro cracks to form in the ceramic. And micro cracks are not good. And the reason is this. So imagine this is a little tiny micro crack, okay? And the material's being stressed. Let's say it's operating as a hydrophone or let's say a driver. It doesn't matter. It works both ways. Let's say you're putting an oscillatory voltage across here and sending out sound. So this is going to happen, right? So what happens when you drive it harder and harder eventually? It touches. What do you think is going to happen there? The spring constant changes. It goes up. You got all these microcracks. They start to touch like this. The material is going to become stiffer. That's a nonlinearity, and it causes problems. One of the worst problems is you could be driving at a pure frequency, but if this thing is bottoming out like this, you're going to generate higher frequencies. Harmonics, we call it. So even though you're driving with a pure frequency, what you get out is multi-frequency, multiples. You know, the frequency, twice the frequency. Typically, you're driving at some frequency, you get out that frequency, twice that frequency, 3 times that frequency, you get out harmonics. And that's usually a bad thing. Now, when the material, so now we got this polarized material, and there's this electric field in there, and that's causing internal stress, and that can decrease in time, and that's what people mean by aging in sonar material. Is that this internal stress is, and this is also due to domain wall migration, Brian tells us. So this has been quantified throughout the book. I don't know if it's in this chapter, but somewhere you'll see that the problem here is that your sonar material its properties are changing. Okay, the resonant frequency is changing. So it causes problems, and typically it's not as efficient. You know, typically it degrades. So people have played around with this. You can read more. You can look in the textbook. They've found ways to kind of reduce how rapid the aging occurs. It's hard to calculate for aging and all these other problems here, things that can change in time. It's very hard to calculate those things. So what people do is they empirically look at them. And there's a lot of literature on sonar, a lot of tables, and the book, even though it's a little book, has a lot of tables in there. You've probably noticed. You're going to notice more and more as we go on in the course. So this has all been quantified empirically. It turns out, one of the problems is you have a transducer and you want it to operate at a big depth, and you'd be worried about just the hydrostatic pressure causing problems. It turns out that's typically not much of a problem. For example, the piezoelectric and permittivity constants of barium titanate, okay, change, it's less than 7% up to a pressure of 10,000 psi. Now, this is 70 megapascals, 700 atmospheres. So for 10 meters per atmosphere, right, that would correspond to 7-kilometer depth. Now this is just approximate, and why is that? This is just basic physics. This atmosphere per meter in water is based on the assumption of constant density of water. As you go deeper and deeper, the density is going to go up. So 7 kilometers is pretty deep. That's like 4 miles. So, anybody know? I calculate this in the fluids course that I teach, but I haven't taught that course in a long time. But anyway, if you get interested, you can look it up and just drop by and tell me. I'm assuming constant density here, right? So this is pretty deep. It's not, what's the deepest? Where is it deep? Where is it, the ocean the deepest? Everybody knows this. Exactly, that's right. I had to look it up today. I thought it was 7 kilometers, but not. The deepest point is, that's right, it's 11 kilometers. I think it's like probably 7 miles, roughly 7 miles. And I can't remember, I think I put this on a quiz in a fluids course that I taught, but it's been so many years. All I have to do is just, take 1 minute to look it up, but I'm too busy. So, I think I had him calculate how much the density went up at the deepest part of the Mariana Trench. So somebody, can you do it? Somebody get interested. I hope somebody gets interested in it. Come by and tell me. Send me a video. I'll watch videos. Everyone watches videos these days, right? Okay. So the hydrostatic compression, when you exert the same pressure in all directions, that turns out to be not much of a problem, which is reasonable. If you want to break a material, what you want to do is you want to exert unilateral kind of stress on it. Stress from all directions is going to be pretty strong in that. That's basically what's going on here, I think. So this is why people use these are the hard ceramics. They keep their polarization when you exert a lot of stress on them, unidirectional stress. Okay, so that's it for this chapter. This and the previous chapters were pretty short, so there's just, as I told you, there's just one quiz on these 2 chapters, and I'll send it out tomorrow after we finish the second part of the problem set. So now, so is this 4?
I think it's 5.
You're right. Okay, so let me do this thing here. Okay, so this is the first problem in the back of chapter 4 here. And here's the idea. And this turns out to be very practical, as I will briefly explain here, and as you will see more of on the quiz. This is one I distinctly remember that I cooked up on the quiz. It has to do with sensitive laboratory balances. The typical operating principle of accurate laboratory balances is the piezoelectric effect. And we'll see that here, okay? And then you'll explore it more in the quiz. All right, so here's a rod. Brian tells us that it's long, so relatively long, which means L is much greater than W or T. This is the width. This is the thickness. It's poled this direction and polarized in that direction, which as far as I know, it's always the case. That the poled direction is the same as the polarized direction. So these are conducting, metallized or whatever, conducting plates have been evaporated onto there or some process. As far as I can tell, we don't make this approximation that L is much greater. I don't know why he put that in there. If you have any thoughts on that, as always, if you have any, I picked that up from Brian Williams, as always. He says it all the time. Well, not lately. He's off the air now. God, this is weird. The news is really entertaining, isn't it? Sometimes strange. But anyway, as always, if you think you understand why Brian said this should be large, relatively long, let me know. I don't see it, and we'll go through the theory. You'll see we don't make this assumption anywhere, and it's a general theory. Okay, so. Okay, now you have to, when you work on problems like this, you have to keep looking back at the theory to remind yourself, okay? This is the Y direction, it's poled in the Z direction, and then the X direction is coming out this way. The force is static. We're told that it's static, but there's no reason why we can't oscillate this this can't be oscillatory. As long as it doesn't get so high that you start to see standing waves, and as long as it's uniform compression and expansion. So it's sufficiently low frequency. And that doesn't have to be, these are solids that the first standing wave mode in here is going to typically be really high frequency, right? Many kilohertz typically in solids. So you should be able to get away with this at a reasonable frequency range, not just DC. But the application is often DC, like the balance. Balance is DC, right? Now let's suppose, just for a little a qualitative argument I'm going to make here, suppose F is positive. This is the positive direction of F. And remember how that's defined? Positive, the stress is going to be the force divided by this area. Positive stress means positive strain in that direction. So this is the positive direction of that. Inward, having a force inward, that's going to cause a negative strain. So that's just the convention. And incidentally, there has to be an equal and opposite force here because we don't want this thing to move. That's okay, we just focus our attention on one side here. Now, F is positive, the bar will it will elongate. It'll get longer in this direction. Now, the idea of the problem here is that this force is going to cause the bar to elongate. But we apply an electric field here such that we keep the bar at its equilibrium length. That's the idea of this problem. And you might think, oh, well, why are you doing that? Well, let me talk a little bit about it, but that's the idea behind a balance. That's what a balance is doing, okay? So we have this force here. The bar is going to tend to elongate. But we apply an electric field here now. What's the effect of the electric field going to be? Well, if the electric field is in this direction, it stretches the material, right? That's going to tend to bring the material to counteract this. Now I have to say tend because you remember the electric field, it's a Poisson type effect for the electric field, but it can go both ways. Remember that? When you exert an electric field here, you stretch the material here, you might think that that electric field causes this to come in, but there are cases that have the material that have the opposite sign where it goes the other way. Remember that? So you have to be careful. But it's all in the math. It's all in the D's. The sign, they can have different signs. So the idea is that we're stipulating that the length stays constant. And that's what happens in a balance. You've got the balance pan. Okay, it's in equilibrium. You put something on there you want to weigh. It's going to tend to go down. Well, there's a sensor in there, very sensitive, probably optical, I don't know. And a feedback circuit that puts an electric field across here to keep the balance always in the same location, always in equilibrium. So you put this down here, it doesn't sink down. Because of this, the piezoelectric action, it stays at where it is. And why is that useful? Well, you're supplying a certain voltage here to do that. That voltage is proportional to the mass. So once you know the sensitivity, you can get a mass, you can get a readout. So you'll be doing that on the quiz, okay? It's very somewhat, and that's the idea of a piezoelectric balance. And there are many of them. It's very common. I've got one, an expensive one. Okay. So here we go. All right. Stress. It's stress-free everywhere except here. There's because this is the y direction. There's a T2. All the other stresses are 0. Okay, and we're stipulating that there's no longitudinal strain. So that means S2 is equal to 0. Okay. I think later on we're going to talk about S1 and S3. We don't need to worry about them right now. All right, so here they are. Okay. Now I don't expect you to write these down in your problem set solutions, but and I didn't write. I copied these from the lecture notes. I think they're also in the book. I think they're in the book. So here are the transduction. The canonical transduction equations for a piezoelectric strain situation. It's not in vector notation. All the components are written out here. So this is in their gory detail here. Here they are. Now we get a lot of simplification. The only stress T that is 0 is T2. And furthermore, the free charge is only in the 3 direction, so D1 and D2 have to be 0. So I'll let you, you should go through I don't think I need to belabor this, but this all collapses down very quickly. And where you start is up to you, but you want to usually start in one of the simpler places. I started with the D3 equation. We need to know, we're going to need to know what this is. You know, this represents, this is a reflection of the free charge in there. We're putting just enough free charge to create an electric field to keep the longitudinal strain constant. So this is of obvious importance to us. So we said, you know, T1, T2 equals 0, we get this. Okay. Incidentally, what you can look is that you can conclude from here that because there's no T's, these T's are 0, there can be no E1 and E2. All right. We don't get it. These are identically 0, the shear equations. Don't have to worry about them. And now we're stipulating S2 equals 0. So there you can see that you get this. Okay. So you can see what's happening here. We're for a specified stress, which is going to be the force divided by the cross-sectional area, right, perpendicular to the force. We're going to require a certain electric field to have no strain in that direction. We've zeroed out the strain here. So we substitute this into here, solve for V, solve for E, and then the voltage, we're making the typical assumption of a uniform electric field. So in that case, the voltage, the work per unit charge, is just the force per unit charge times the distance. So we use this all the time. We've already used it a lot, and we're just going to keep using it. So for the uniform field assumption, we have the electric field, which we can get from here, times the thickness, and we get this. And we substitute for the stress, and now we have, once you specify a force that you're exerting to stretch this thing, this is the voltage that you would apply to keep the bar from straining in that direction. Now it's got a minus sign here. However, D31 tends to be negative. What happened in the lab when you guys did this? The last lab. Did you measure D31? You did, I think.
3.3.
Oh, 3.3. Okay. Sorry. So D31 tends to be negative, but it's not always negative. So taking that typical case, though, of this being negative, you can see that it's a positive voltage. So that confirms our qualitative argument earlier, that when we stretch the bar this way, exert a force this way, we want to put an electric field this way, which would be a positive voltage. But it's not always positive. It depends on the material. Okay. Now the second part of the problem, I think, asks, are all the strains 0? See, we've specified that there's no strain in the y direction along the bar. What about the strains? Well, at this point in this course, you're naturally suspicious, right? And you'd be right. So here are the equations from our transduction equations. Here's the S1 and the S3, where there's only a stress in the 2 direction or y direction. Here's what we get. And now you can see here that even without an electric field, well, this could cancel, but they're not. You can see that we don't have an isotropic solid. So with an isotropic solid, you can stress it one way and, I'm sorry. I'm going overboard here. So why is this here? It's really simple. Look at this. Focus your attention on this. This has got to be there. Forget what I said about isotropic. That was wrong. That's just Poisson's ratio effect, right? We stress in the 2 direction. So this is going to involve Poisson's ratio. So we know that's there. So the issue becomes, can these things possibly cancel? We get similar in the 3 direction. Very similar in the 3 direction. There is a difference now, though, because that's the direction where the electric field is, so it involves D33. So we need to reduce this. You know, maybe these things cancel, right? So how do we do that? Well, we should put it in terms of one independent variable. The natural independent variable here is the force F. So I'm going to do that, okay? So T2, remember, is the force divided by this. So we could have used T2, you know, but I did it in terms of F, okay? And we know what E3 is. We just found E3 in terms of F, right? So that's probably what we already had this in terms of F, so I'm going to put that in terms of F. So when you substitute these into here, the strain in these directions is going to be proportional to F. It has to be, because this is all linear. We're assuming linearity here. So it's proportional to F. And the interesting thing here is the coefficient, right? And here we see is, okay. So this looks like we could get 0 here. However, I'm a little worried now. I'm stating here that these have opposite signs, right? So this is the usual, you know, Young's modulus, for example. This will be related to Young's modulus, 1 over Young's modulus. This is going to involve the Poisson's ratio, right? Now the definition of Poisson's ratio, a minus sign is included, so you're not dealing with for Poisson's ratio. So now I'm concerned here, is the same thing hold true? Is this going to tend to be the same sign because of the convention? I don't know, I have to check. I all of a sudden realized that I don't know what's going on here. Let me make a note and I'll check it. I'll check that. But anyway, assuming this is right, what I said here, okay, then you can see that if they have opposite signs due to the Poisson's ratio effect, okay, assuming that, then you can see these things can't cancel each other, right? So we always have an S1. You can't. You know, you can't defeat it. It's going to be there. What about S3? Well, it's the same analogous analysis here. Just involves different, you know, S13 and D33. Now, these have opposite. I'm again saying that, assuming these have opposite signs, the S's here. The D33 and D31 usually have opposite signs. So now in the typical case, this could be 0, but it would be a coincidence. You know, these are pretty much independent quantities here. So if it were 0, you know, it'd be a coincidence. But it could happen at some frequency. You know, the problem is stated as DC, but it works at sufficiently low frequency. Okay, so we've now seen a number of examples. This stuff is probably starting to sink in of how we deal with these, what looks like, you know, hopelessly complicated equations. When in simple geometries, we can beat this down and get out useful information, quantitative information. Okay, any questions about that problem? Okay, is this the first cylindrical geometry that we've done in this class? I was thinking about, yeah, all right. This is really common. This is a preferred geometry. And you'll see this more and more as we go on, okay? Particularly hydrophones. Very common. So here's the idea. So you're thinking, oh, we got to use cylindrical coordinates. No. We're going to make the typical assumption here that when thickness here is relatively small, that means B minus A is relatively small compared to the radius here, which is roughly true here, right? Then this thing is going to act like, it'll be essentially a plate. In other words, you can imagine making a cut here and bringing this thing out. It's not going to really change things much. Now, when the thickness is comparable to the radius, then you got to go to curvilinear coordinates. It's no longer, and I think we're going to do that later on in the course in hydrophones. I can't remember. But for right now, here's the idea. I should have specified the problem here. We typically call, as I've told you before, the z direction is the direction of polarization and electroding, right? So it's polarized in the z direction now, but it happens, this is not a constant. Over here, when we come out here, the polarization is going to be that way, right? But the fact that this is thin means it's essentially a flat. It's going to behave like a flat plate. The curve nature here, the curvature here is going to have a negligible or small effect on what's going on. So the z is the polarized and pole direction. This is L, and we have this, and in this problem we're applying 100 DC volts. Okay, so this is radial polarization. We're applying 100 volts. So the width of our plate here, imagine taking this, like I said before, and opening it up, right? We need to know that dimension. Well, it's just the circumference, and we choose the average circumference to make it a little bit more accurate. We're going to take the average radius here, multiply it by 2 pi. Yeah, there's the 2, that's the average. So we take the average radius, just makes it a little bit more, A and B are close, but they're not all that close here, right? We're making a pretty rough approximation here. So it's good to use the average circumference here, and that's going to be our width. And that's in the x direction, okay? Because imagine unfolding this like that. So we have essentially a plate here. We'll use this trick a number of times in this course. And now, so we want to find what changes in the length, mean diameter, and wall thickness if no forces are applied to the cylinder. So why are they going to change? They're going to change because we put some voltage across here. And it's stress-free. Okay, so what's, now this is nice. All of the stresses are 0. That's going to greatly simplify things. Furthermore, the D, which is dictated by free charge, is just going to be a D3. No free charge in the 2 in one direction, so D1 and D2 are going to be 0. And now if you look at those previous equations, here they are, right here, and specialize them now to where we have a lot of zeros. What you get is this: no shear action, no transverse electric field, transverse to the direction of polarization. We've got a Poisson's ratio, and Poisson's ratio, the analogous electrical kind of effect here going on. Oh, that's right, there's no stress, so it's purely electric here. Right, and same thing in the polarized direction. So we do a similar idea of what we did before. The voltage, we need to connect this with the voltage because that's what our drive variable, the convenient drive variable is here. So that's going to be, just as before, the electric field, E3 times the thickness. There's the thickness. We can substitute in this case we're going to find the electric field because then we can substitute it into here and find the strains. That's what we're after. So the electric field from here is going to be given by this, the 3 direction. We know all these numbers, we might as well compute it. That's what it is, volts per meter. In volts per meter, here it is. And now we can find quantities like S3. This is the strain in the polarized direction. Remember, the strain is the relative change in distance. So if I have 2 points here, and let's say I stretch this, the strain is the new length minus the original length. So strain is dimensionless. So the strain in the 3 direction, we're told from here, is D33 times E3. You want to look this I don't know if we've started to do this before, but we're going to be doing it more and more. Look up values. We're given the material. I can't remember what it is. We're assuming it's, type 4. We're assuming it's Navy type 4. So you look up parameters, look up D33, calculate this, and we get, this is called microstrains. Okay, it's microstraining. And this is not unusual. The strain is on the order of a millionth. Okay, so sometimes people call it microstrain, just to give you a rough, qualitative picture of what's going on. So it's about in the millionths there. What about S2 and S3 in the transverse direction? Well, similar calculation. We got a minus sign here. It's in the opposite direction. And again, it's microstraining, but a different number. So remember, these are tensile strains here, and they're how this is the displacement. I said that, the new length minus the old length. Or maybe I didn't say that right. Can we play it back? No, I'm just kidding. When you stretch this, you take the change in distance divided by the original length, right? It's dimensionless. I don't know if I said that right before. Monday mornings are really bad for me. Okay, so here's what it means. Use the displacement. So it's the relative displacement. The change in distance then, if we wanted to know the change in distance, we need to bring this over to this side equation. We need to take the strain and multiply by the length to get the actual change in distance. So the change in equilibrium length is going to be given by this. So we take our microstrain here, our particular value of S3, multiply by, this is for the change in thickness. Is that? Yeah, that's the first one we did. Right, so this is the thickness, remember, the polarized direction. Multiply by the thickness, and we get 29 nanometers, 30 nanometers. Pretty tiny, right? But remember, when this thing's in water, water's very stiff, right? You can send out, that could send out maybe, I don't know, I don't know the numbers, but it could send out a healthy sound wave in water. What do you think is going to happen? What do you think would happen in air with those kinds of displacements? I don't think you're going to hear anything. That's what's got me concerned about the racquetball, among other problems with it. But it has to be tried. We just got to try the racquetball. It might work in air. Okay, so the racquetball painted with silver paint. I've only talked about it about 10 times. So okay, I don't need to remind you. Okay, so anyway, there's the change in thickness. It's tiny. Oh yeah, and I expressed it. So it's common down here to express it in convenient units. So we usually write this. We don't keep it like this. We put it in nanometers. It's common for people to do that. What about the change in length? Well, it's the same idea. Now it involves S2, and we need to multiply by the length. And now we get more than nanometers. Now we get typically microns. Okay, in that case, because L is due, I guess, primarily to the fact that L is a factor of, the fact that L is significantly greater than the thickness. So now that's given us roughly a third of a micron. Okay. Finally, the diameter, you have to actually think about this a little bit. Because we've gone rectangular on this, right? We've taken this thing and opened it up and treated it like a flat plate. So we know we've been dealing with the circumference, which we call the width, the mean circumference. We call it the width. So you need to get the diameter from that, you just divide, the circumference is pi times the diameter. So we need to take the change in mean circumference divided by pi to get the change in diameter. And that's what I've done here. Okay, you can check this. And as always, if there's a problem, let me know. So we've simplified this, and now we get about a tenth of a micron for the change in the mean diameter. It's the mean diameter because we're using the mean circumference here. Sorry. Okay, now there's more to this, right? There's a part B here. Now, this is kind of interesting. So now suppose we block this. We don't let it change its length. We have 100 volts here, but we're demanding that this doesn't change its length. We're fixing that. We're mechanically blocking it. And how hard is it to do that? Well, we're going to find out. We're going to get an indication of that, because we're going to find, I think, the force required to block it. That's usually what people find here. What forces can be generated? Yeah, basically the force here. So, here's the idea. The script L is going to be constant. Okay. Now, so we now have a stress. We're going to find what that stress is. But we have no strain in the two direction. Right? Before we had no strain, but we had a, before we had no stress, but we had a strain. Now we have a strain. Now we have a stress, but no strain. Now we have the opposite. Okay. So we look at S2. We're interested in S2. We look at the general relationship, and it's easy to see here that the stress in this case, now we have zero strain. We can find the stress is given by this. We know all this, okay? So we can find the stress, but what we're really interested in, and we have a better feeling for, is the force. So I'm going to multiply the strain. Before I plug the numbers in, usually you want to, often in these problems you want to stay algebraic until near the end when you start to plug the numbers in. Because you can get simplifications, and it's useful to have algebraic quantities. You know, they're general. So you don't want to plug, usually you want to not plug in numbers immediately. So that's what I'm doing here. I'm keeping this and I'm multiplying by the cross-sectional area. There it is. We want to be careful here, right? You see this? You see the thickness there? I'm taking the, and sometimes I know students have trouble with this. I've seen this. This rings a bell. So what's this area here? That's relevant because of the stress. Okay, in the L direction. So it's the, of course, it's the area of this circle minus the area of the inner circle. Okay, so it's pi r squared. It's pi a b squared minus pi a squared. That's the area. So you can see that right here. So now I got this formula, and I plug. Now I know everything, and I know all those parameters. So I plug in the numbers, and I get 176 newtons. Most people, including me, don't have a feeling for a newton. So we have an equivalent mass. So this force is going to correspond to the weight of a mass in the Earth, near the surface of the Earth. So I take this value and divide by G. People do this all the time. Okay, this is the mass equivalent of this force, and I get 18 kilograms. And you probably know that's pretty heavy, 40 pounds. Yeah. So this is that's actually, I think, kind of impressive, because this is pretty tiny, isn't it? This is pretty tiny. And so it can support, you know, it can, how do you want to say, it can lift. You know, if it can support it, it can lift it an extremely small amount. But it can lift 40 pounds with 100 volts across it. That's not a lot of voltage. 100 volts, not a lot. So that's pretty impressive. We're talking about big forces here, which is what you want, you know, when it comes to an underwater projector. So we'll finish the third problem tomorrow, and then we'll get into the next chapter.
With that picture there, can you? I don't think I understand which way the force is going and why the area you chose was the.
Okay, we've taken this. First of all, you want to appreciate we've taken this and we've opened it up,
right.
So it's a plate, and the voltage is being applied here, but we're interested in the force. It's blocked this way.
Okay.
Yeah, it's blocked transverse, right? It should be S2. Yeah, this is 2. It's blocked in that direction. It's transverse to the electric field.
Okay.
Right. So it's pretty impressive. Yeah, this is strong forces here involved. That's why it's used for sonar material. Okay, anybody have any questions or any general? Oh, we actually finished on time. That's unusual. Okay, so we'll finish the problem set tomorrow and get into the new chapter.